Hello, my dear students. Welcome to IKSR chemistry classes. Here we are in lecture number 3 on electron transfer reactions. In this video, we will discuss the factors affecting the rate of electron transfer reaction by outer sphere mechanism. The rate of an electron transfer reaction by outer sphere mechanism depends on the molar concentrations of both oxidant and reductant as follows. Rate is equal to K into molar concentration of oxidant into molar concentration of reductant. At the same time, the rate also depends upon K. The rate of reaction also depends on the velocity constant K, which in turn depends on the Gibbs energy of activation delta GH, that is the activation energy, that is EA of the reaction. The rate of electron transfer reaction by outer sphere mechanism depends on the molar concentrations of both oxidant and reductant. At the same time, the rate of reaction also depends upon the velocity constant or rate constant of the reaction, and the velocity constant depends upon Gibbs energy of activation, that is activation energy of the reaction, as per Arrhenius equation. It is the exponential form of Arrhenius equation. K is equal to A into e to the power minus E by RT, and it is the logarithmic form of Arrhenius equation. Log K is equal to log A minus E by 2.303 RT. Higher the value of delta GH, that is activation energy, higher the value of activation energy, a smaller will be the value of K, and lower will be the rate of reaction. Thus, it is obvious that the rate of second order electron transfer reaction by outer sphere mechanism depends upon the Gibbs energy of activation, that is activation energy of the reaction. There are various factors which contribute to Gibbs energy of activation and hence affect the rate of electron transfer reaction by outer sphere mechanism. All those factors which contribute to Gibbs energy of activation of electron transfer reaction by outer sphere mechanism affect the rate of such reaction, and these factors have been summarized below. Electrostatic repulsion between similarly charged coordination spheres of reactant complexes, identity and concentration of ions in the reaction medium, reorganization energy, Gibbs energy of the reaction, and nature of ligands. These 5 factors affect Gibbs energy of activation of electron transfer reaction by outer sphere mechanism, and hence these 5 factors affect the rate of reactions. Let us consider these 5 factors one by one. The first factor is electrostatic repulsion between similarly charged coordination spheres of reactant complexes. The electrostatic repulsion between similarly charged coordination spheres of reacting complexes contributes to the activation energy of the reaction. If we bring similarly charged coordination spheres of reacting complexes from bulk together, some work is to be done against the electrostatic repulsion force, and it contributes to the activation energy of the reaction. greater the electrostatic repulsion between similarly charged coordination pairs of reactant complexes, the greater will be the activation energy of the reaction, and consequently slower will be the rate of electron transfer reaction. The second factor, identity and concentration of ions in the reaction medium. If the reactant complexes are negatively charged, the rate of electron transfer reactions by outer sphere mechanism increases with increase in the concentration of positively charged ions in the reaction medium. And if the reactant complexes are positively charged, the rate of electron transfer reactions by outer sphere mechanism increases with increase in the concentration of negatively charged ions in the reaction medium. This is due to the fact that the oppositely charged ions constitute ion pair. If two oppositely charged ions are brought together, they constitute ion pair. It decreases the energy of transition state of the reaction by decreasing the electrostatic repulsion. And in other words, it decreases the electrostatic contribution to the activation energy, and hence it increases the rate of electron transfer reaction. If two oppositely charged ions are brought together, the potential energy of the system decreases at a certain point. It decreases the electrostatic repulsion in the transition state, that is, decreases the energy of transition state and decreases the activation energy of the reaction, and hence increases the rate of reaction. The presence of ions having opposite charge to the reacting complexes decreases the activation energy for the reaction, and hence increases the rate of electron transfer reaction by forming ion pair. And third factor is reorganization energy. The electron transfer reactions by outer sphere mechanism takes place more slowly when the oxidant and reductant differ widely in bond lengths, geometries, or solvent cell. Under these conditions, Gibbs energy of activation for electron transfer reaction will be high due to greater inner sphere reorganization energy and greater outer sphere reorganization energy. It means if the reactants of an electron transfer reaction differ widely in bond length, geometry, or structure of solvent cell, greater will be the amount of reorganization energy, which is of two types: inner sphere reorganization energy, which is due to change in bond length before electron transfer, and outer sphere reorganization energy. This is due to change in the structure of solvent cell during the formation of transition state outer sphere complex. In the case of octahedral complexes, the bond lengths change more abruptly. That is, delta D will be high when Eg electrons are being transferred. It may be noted that in octahedral complexes, the bond lengths change more rapidly, more abruptly. That is, delta D will be large when Eg electrons are being transferred. This is due to the fact that the lobes of Eg orbitals lie along metal ligand direction, and consequently slower will be the electron transfer reaction. If delta D is high, greater will be inner sphere reorganization energy, and the greater will be Gibbs energy of activation, and hence slower will be the rate of electron transfer reaction by outer sphere mechanism. If Eg electrons of metal ion are being transferred because its lobe lie directly along metal ligand direction. This is dz square orbital. This is the ligand. dz square orbital contains one electron. There is electrostatic repulsion between electron of d orbital and electron pair of ligand, and therefore this distance is longer. And if this electron present in Eg orbital is lost, there will be no repulsion between the electron of metal ion and ligand. As a result, the ligand can approach the metal ion more closely and metal ligand distance will become shorter. If Eg electrons of metal ion are being transferred, the metal ligand bond length changes more abruptly. Delta D will be larger and greater will be inner sphere reorganization energy, and consequently the slower will be the rate of electron transfer reaction by outer sphere mechanism. The following outer sphere electron transfer reaction takes place very rapidly, having the value of K is equal to 10 to the power 5 liter per mole per second due to very small d. This is the reaction FeCN whole 6 4 minus, having leveled iron atom, and FeCN whole 6 triple minus, having non-leveled iron atom. Its electronic configuration is T2G6 with plus 2 oxidation state, and its electronic configuration is T2G5 with plus 3 oxidation state of iron. This electron is transferred from Fe2 plus ion of this complex ion from T2G6 orbital to T2G5 orbital. As a result, its electronic configuration will become T2G5, and one electron will increase in this set of orbital. It will become T2G6. The value of D, that is change in metal ligand bond length during the formation of transition state before electron transfer, is very small, and therefore this reaction takes place very rapidly. Its velocity constant is 10 to the power 5 liter per mole per second. Because T2G electrons are involved in the electron transfer reaction, delta D is very small. On the other hand, the following outer sphere electron transfer reaction takes place very slowly due to large delta D. This chemical reaction involves the transfer of electron from leveled cobalt 2 plus ion to non-leveled cobalt triple plus ion. As a result, leveled cobalt is oxidized from plus 2 to plus 3, and non-leveled cobalt is reduced from plus 3 to plus 2. Its electronic configuration is T2G5Eg2, and its electronic configuration is T2G6Eg0. It is low spin complex, while this one is high spin complex, and this happens due to its lower oxidation state, and it is a lower spin complex due to higher oxidation state. If this electron is transferred directly from Eg2 to Eg0, the electronic configuration should be T2G5Eg1, because one electron has been transferred from Eg to here, and its electronic configuration should be T2G6Eg1. Cobalt plus 2 should form high spin complex, but it is not a high spin complex. if it were high spin complex, its electronic configuration should be T2G5 Eg2, but it is T2G6 Eg1, and it should be lower spin complex. It is again not a lower spin complex, because if it were a lower spin complex, its electronic configuration should be T2G6 Eg0. Thus both the products are in electronically excited state. It should be lower spin complex, but it is not a lower spin complex. It should be a high spin complex, but it is not a high spin complex. And both the products are in electronically excited state. If the transfer of electron takes place directly from Eg set of orbitals of labeled CONH3 whole 6 2 plus to Eg set of orbitals of non-labeled CONH3 whole 6 triple plus, both the products will be in the electronically excited state as shown above. When these electronically excited products will return back to the ground state, the excess energy will be emitted in the form of energy, and the reaction should be exergic, that is delta G should be negative. But it is not true. Actually, delta G is equal to 0. It means both the products are not in electronically excited state. Therefore, it has been suggested that both the reactants undergo electronic rearrangement before electron transfer to have more product-like configuration. And this electronic rearrangement requires some energy, which increases the Gibbs energy of activation of the reaction and slows down the rate of reaction. This electronic rearrangement also contributes to the Gibbs energy of activation of the reaction of electron transfer reaction by outer sphere mechanism. This is why the above electron transfer reaction takes place very slowly, having the value of velocity constant equal to 8.0 into 10 to the power minus 6 liter per mole per second. Because both the reactants should undergo electronic rearrangement so that in the transition state they may become more product-like, and this electronic contribution, this electronic arrangement requires some energy which contributes to the Gibbs energy of activation of the electron transfer reaction by outer sphere mechanism. Gibbs energy of reaction. The greater the negative value of standard Gibbs energy of reaction, the greater the negative value of standard Gibbs energy change delta G naught of the electron transfer reaction by outer sphere mechanism, the lower will be the Gibbs energy of activation, and consequently faster will be the electron transfer reaction. Greater the negative value of standard Gibbs energy change of the reaction, a smaller will be the Gibbs energy of activation. It has been illustrated with the help of following figure. This figure is for electron self-exchange reaction in which the reactants and the products are identical. These are energy profiles for electron transfer reaction by outer sphere mechanism, and it is for electron self-exchange reaction in which reactants and products are identical. Potential energy has been taken on the y-axis while reaction coordinate has been taken on the x-axis. This is the potential energy diagram for the reactants, and this is the potential energy diagram for the products. It is the transition state and it is Gibbs energy of activation of the reaction. These two potential energy curves don't cross each other due to mixing up of wave functions of reactants and products. As a result, the wave potential energy curve of the reactants bends from point B downwards, and we get two separate energy curves, this one, and not two parabola crossing each other. The separation between these two solid curves is called 2HAB, which is the measure of degree of mixing up of wave functions of reactants and products. The reaction proceeds. Initially, the reactants are at position A, which go to the position B. This is Frank-Condon energy barrier, and then rolls down to potential energy well C. It is called potential energy well. The reactants are initially in the potential energy well A. They move upwards in the potential energy diagram, forming the transition state, and then rolls down into the potential energy well of products. This is the direction of reaction. This is the path of reaction, A to B to C. The dashed lines indicate the path of potential energy curve if there were no mixing up. This diagram is for heteronuclear redox reaction, electron transfer reaction. Here, the value of delta G is 0. The value of delta G. Both reactants and products have the same Gibbs energy, and hence delta G is 0, and this Gibbs energy of activation is high. But in the case of heteronuclear electron transfer reaction, delta G is negative because the products have lower Gibbs energy while the reactants have higher Gibbs energy. Delta G is negative and the Gibbs energy of activation is smaller. In this case, the reactants can go to the transition state and roll down into the potential energy well of products more efficiently, and there is very little chance of the products to be transformed into reactants. C to A, the probability of going from C to A is very low, while in this case the probability of going from C to A is high. Therefore, in this case, heteronuclear redox reaction takes place more efficiently, more rapidly, because its delta G is negative and Gibbs energy of activation is low, and there is greater probability of reactants to be transformed into products. The figure A is the energy profile for the electron transfer reaction, electron self-exchange reaction, in which reactants and products are identical. The curve is symmetric because reactants and products are identical. It consists of two energy curves for the wave functions of reactants on the left hand side and the wave functions of products on the right hand side. These two curves don't cross each other. This is due to interaction or mixing of wave functions of reactants and products. It results in two separate energy states instead of two parabolas crossing each other. Two parabolas don't cross each other. They bend away from each other, and it results in two separate energy states. The dashed lines represent the course of parabolas if reactants and products don't mix up together. The energy separation between two solid curves is denoted by 2HAB. It is the measure of degree of mixing. Greater the degree of mixing, greater will be 2HAB, and smaller will be the Gibbs energy of activation. The path of reaction. The path of electron self-exchange reaction may be regarded as the motion of a point from potential energy well A of the reactants up to the Frank-Condon energy barrier B, and then down to the potential energy well C of the product, as we have discussed here. A to B to C. A to B, this is Frank-Condon energy barrier, to C. Figure B is the energy profile for the heteronuclear electron transfer reaction involving delta G is equal to negative. As a result, delta GH is lower. 2HAB is greater. The interaction between reactants and product wave function is greater. The reactants roll down from Frank-Condon energy barrier B to the potential energy well of the product C more efficiently, and heteronuclear electron transfer reaction takes place more rapidly than electron self-exchange reaction. This is due to greater mixing of potential energy curves of reactants and products, greater the value of 2HAB, a smaller delta GH, and greater the rate of reaction. And the last factor is nature of ligands. The pi acceptor ligands such as bipyridyl, tripyridyl, cyanide ion, phenanthrene, etc. delocalize the electrons of the metal ion due to their ability to form metal to ligand pi bond. These pi acceptor ligands can delocalize the electron of metal ion to a greater extent due to their ability to form metal to ligand pi bond. It decreases delta GH, increases electron transmission coefficient kappa EL, and hence increases the rate of electron transfer reaction by outer sphere mechanism, especially when T2G electron of metal ion is being transferred. And this is why bipyridyl, tripyridyl, phenanthrene, and cyano complexes of ruthenium 2 plus or 3 plus, Fe 2 plus or 3 plus, and vanadium 2 plus and 3 plus, etc. undergo electron transfer reaction much more rapidly than corresponding aqua, amine, and ethylene diamine complexes. It should be omitted, it has been repeated. The bipyridyl, tripyridyl, cyanide complexes or phenanthrene complexes of these metal ions undergo electron transfer reaction by outer sphere mechanism more rapidly than aqua, amine, and ethylene diamine complexes, because these pi acceptor ligands can delocalize the electrons of metal ion more efficiently due to formation of metal to ligand pi bond. It increases the value of kappa EL, electron transfer coefficient, electron transmission coefficient, that is, increases the probability of transmission of electron from metal ion to from reductant to oxidant. It may be noted that the value of kappa EL varies from 0 to 1, and when there is greater overlapping of orbitals of metal ion and ligand, the value of kappa EL is higher. Thank you for watching the video with concentration. Please like, share, and subscribe it. Thank you again.